Welcome DC Circuit students. In this lab demo we're going to look at the effect of multiple sources joined in either series or parallel, and we're going to also look at the effect of the load circuit, and that's the circuit that includes the thing you're powering with the source, usually something you're going to use, your electronic circuit or a motor or something like that. The effect of the impedance of that circuit on how sources combine in series and parallel. In general, as you probably learned from your theory, if we combine two sources in series, their effect will be additive. In DC, they'll just be straight additive. If, as you'll see in AC, they'll be additive to the extent that they're in phase. And in parallel, the voltage will basically default to the highest voltage, or will be the same if we have the same voltage in both sources, but the current capability of the source will double. Now, that doesn't mean that our load circuit doesn't follow Ohm's law. Basically, the amount of current flowing through our load resistor, our load circuit, will be defined by Ohm's law. So we'll take the voltage of our source, divided by the resistance of our load circuit, and that defines the current. Where the advantage of a parallel source comes in is when the load resistance is so low that the internal resistance of the sources becomes dominant. That's when you'll start to see the impact of a parallel source, or in the case of a battery, you'll see that in the duration under which or over which we can keep providing that current, otherwise known as capacity. So, like I said, this is the demo part of it, and we're going to use a very real battery source. These are 9-volt alkaline batteries, and we're going to use one, and then we're going to add another. These are partially discharged, so they are 9 volts nominal. They started out when they were fresh at about maybe 9.4 volts, and now their open circuit is 8.63, both of them. So I have two batteries that are partially discharged. Now, the impact of the partial discharge doesn't just change the open circuit voltage, it increases the internal resistance in each battery. So basically what I've done here is I've put a resistor of probably somewhere between 10 and 100 ohms in series with this, without adding it to the outside of the battery. It's inside the battery. So this battery now comes equipped with its own internal resistance, which is not so good if I want to power a circuit. So in this case, what I have is a single resistor on my protoboard, and this is a nominal 5600 ohms, so a 5.6K. It's actually 5.56K as measured with the ohm meter. So this is what would be known as a high impedance load. The circuit itself doesn't allow a lot of current. So the Ohm's law says we should be getting 8.63 volts divided by 5.56 times 10 to the third. That would give me my current. So I'm going to go ahead and measure what my actual current gets, what my actual current is, because if, as I suspect, I have added some internal resistance, the resistance of my circuit is actually much higher, or somewhat higher, than what I'm getting. But it may not be so high that it matters, given how much resistance is being provided by the circuit itself. So we have, again, a high internal resistance source, single source, driving a high impedance load circuit. And so I'm pointing to my 5.56K resistor. So I have my multimeter on volts DC. Remember, using the proper hookup. And I'm going to start by just confirming open circuit. So I've put a couple of test leads here, and I'm going to have to hold my meter up each time. So yes, it is indeed what I thought it was. So the circuit is open This would be the connection point. So now I'm going to add a jumper, and I'm going to close the circuit and allow current to start flowing. And I'm going to confirm the source voltage under load. So this is, so you can see now we have 8.61. So we are seeing the effect of that higher internal resistance and the fact that we can no longer maintain open circuit voltage because we have current flowing. We don't have a lot of current flowing because we do have high impedance. So we can note that down. 8.61 volts. Now we're going to measure the current flow, and for that we're going to reconfigure our meter. Very robust banana plugs. So as you can see, I have opened the jumper, so now the meter is going to become the connection point between those. The battery is still hooked up, but it's not flowing any current because I have opened the circuit. And now I'm going to place the meter in series. The meter is the jumper now. So you can see we are measuring 1.56, and it's reasonably steady. We're not seeing it drawing down in spite of the fact that the battery is somewhat exhausted. Okay, so now we've reopened the circuit. So that is the characteristic of a single source with a fairly high impedance circuit. So if we were to look at, okay, let's put another battery which has the same nominal open circuit voltage, what would happen if we put that battery in parallel? You know, are we effectively going to get, are we going to get double the current? Probably not, because we are fairly close to what Ohm's law would limit us to. So in fact, let's do a quick offline calculation. Always good to calculate while you're in the lab. So in our single source circuit, we ended up with 8.61 volts supply. We know we had a 5.56 times 10 to the third resistor. So if Ohm's law were operative, we should have gotten just about what we measured. I calculated about 1.55 milliamps. I measured 1.56. That's actually a little bit more. So what that is telling me is that in spite of the fact that I have fairly substantial internal resistance in this battery, it's nothing compared to the impedance provided by my load circuit. So my load is effectively the rate limiting step, or the high resistance point in series for the current. So with this scenario, I could add another source in parallel, and it probably wouldn't change anything because the resistance of the battery is not what's limiting. But let's just hook it up and confirm that. So I am going to use my measurement point now to add a second source in parallel as a second battery with a second set of alligator jumpers, because I have stranded wire. Okay, so I have the positive of one battery and the positive of another, both going into the positive rail of my protoboard, and I have the negative and the negative going into the negative rail of the other. So they are connected in parallel. So I'm going to take my meter again, and I'm going to measure current. I'm going to measure DC current. So if you have a meter that defaults to AC, remember to push the toggle button to make sure you're measuring in DC. So I'm going to do the same thing. And if, as I suspect, I'm limited by the resistance of the load, I shouldn't really get substantially higher current with the double source. And at 1.57, a little bit more, not substantially. So maybe there was a very, very small effect, but generally we are well within the error of the meter at this point. So I can even just jot that down, 1.57 milliamps. So I'm going to break that. I'm going to leave my two resistors, or excuse me, my two sources in place, and I'm going to pause the recording, and I'm going to change this resistor to something that is smaller. So we're going to see what happens if we go to a situation where we have the resistance of the source possibly being a bit more limiting in our circuit. Okay, we are back with a new load resistance. So I've replaced the nominal 5.6K resistor with an 82 ohm. This is very, very low. So now the load resistance or the load impedance is low, possibly low compared to what may be the internal resistance of the battery. And I've dropped back to my single source. I still have the circuit configured such that I can measure current, and I have my meter configured for current. So I'm going to see what kind of current I measure now with this much lower resistance in the circuit, lower load resistance, and just jot it down, and then I'm going to reconfigure and put that second source in parallel and see if there's any change. As we saw with the high impedance circuit, one source in parallel, two sources in parallel, even though we knew those sources had a fairly high internal resistance, didn't really matter in the current that flowed through the load. And we hypothesized that was because the load resistance was dominating. So now let's see what happens when the load resistance isn't so big. And in this case, I'm going to only close the circuit, even through the meter, fairly briefly, because this is a fairly low wattage resistor, and I definitely don't want it to have any kind of seriously high currents flowing for any period of time. And this may be fairly high compared to what it's rated for. So I'm just going to make our measurement quickly, and I'm going to call it out without showing it. Let me make sure it's this. Hooked up. Everything's continuous. Okay, now we're going to make the measurement and I'll call it out. Something was not continuous where it should be. Okay, so I'm connecting, and my meter is reading about 94 milliamps and 93.6, 93.5, and it's dropping quickly. So that fairly fast reduction is indicative that we are being affected by the increasing internal resistance of our source. And that is very characteristic of an electrochemical source that is depleting, especially alkaline type batteries, the small primaries. So we'll just round that off. We'll say that was approximately 94 milliamps and dropping quickly. So let's see what happens. And again, we're not gonna let that current flow very long, because that's quite a bit of current, especially for that type of resistor. So now we're going to look at the impact of the parallel source. And if we are now at the point where our load resistor is limiting, we should see a significant increase in the current that we measured. And it shouldn't drop quite as quickly. Not that we're going to leave it connected for very long. For these types of currents, it would be ideal to have a bigger power capability resistor. And in fact, making sure this isn't hot there. Okay, so we're going to make the measurement again with two sources in parallel. We are driving with the same circuit voltage. It's still the nominal, the 8.63 open circuit probably much less under load, but now we have two sources capable of contributing current in the event that a single one, was being limited by its own internal resistance. So initial is 9.6 and holding 96, excuse me, and holding fairly steady. So we didn't get a vast increase, but we didn't get the dramatic drop that we did with a single source. So compared to a single source with the fairly low load resistance, we had a little bit higher measured current, and we held on to it a little bit better. And we'll note that down. So we'll say approximately 95. So that's nominally the same. So the big difference is it was a steadier current and not dropping. So let's go ahead and compare that to what we would expect via Ohm's law for using an open circuit 8.63 volts and our nominal 82. So according to Ohm's law, if our load circuit were the only thing limiting, we should have been able to measure about 105 milliamps. And so even with our dual source, we could only get 95. So now we're beginning, unlike the case where we used the 56K, or excuse me, 5.6K load resistor, now we're beginning to see how having low load resistance we were beginning to see the impact of our depleted source, our higher internal resistance in our source, and now we're beginning to see the impact of the advantage of the parallel source. So we're going to go back to our higher resistance here, simply because that's going to keep our currents down in the realm where we can operate them better in steady state. And last but not least, we're going to confirm the effect of operating in series. And that's the configuration that is more typical of what you would use for an electrochemical source. So for our series connection, we're basically going to put positive to positive, negative to negative for the batteries. So we need one fewer lead. So if I establish this point in my circuit as like ground 0, I have that being connected to the negative of this battery, then this battery is going to give me a boost of somewhere around 8.6 volts, and now I'm going to give a second boost by connecting a second battery. So basically the top of one is now at the bottom of the other. Those are isopotential because I just hooked them together. So now I'm going to get another 8.6 volts. And if I wanted to confirm that, I should now be measuring something above 17 with my multimeter at open circuit. The circuit is open here. So if I use my measurement points, I am getting basically what I would expect the two open circuit voltages added. So 8.63 times 2 within meter error. So I now have 17 volts that I can drive the circuit with. And again, I have a fairly high resistance in the load itself. So the last thing to check is to check what does that do with my current? And will the circuit basically follow Ohm's law, or will it not deliver as much current as I expected because of that? Remember, we're dealing with a couple of sources that are somewhat depleted, and they have their own resistances. So how does that affect things compared to our fairly significant, back to our 5.6K So if I measure current, let's measure some DC current. We can see that we're getting a fairly steady 3.11 milliamps, and that is in fact what would be predicted by Ohm's law simply based on the load circuit. So the impact of that internal resistance of the depleted source isn't showing up even if I put them in series. So I didn't need to use a parallel connection to give me the current that I would expect for this circuit with the higher impedance. So what we've demonstrated is if we have a high impedance or a high resistance circuit, the impact of the source is less important with respect to current supply capabilities. If we put our sources in series, the voltages add. We get the same current that we would get from either one, but we'll be driving our circuit with a higher voltage. So Ohm's law in the circuit will predict our behavior as if we were using an ideal source. If we have our sources in parallel, then the current that actually flows through our load will depend on the magnitude of that load versus the magnitude of the internal resistance of the sources. And this doesn't just affect batteries. Sometimes small instrument supplies like a USB function generator might have very low current capabilities, and so your predicted current from Ohm's law from your circuit might be much greater than what you actually get if your circuit has a low load compared to the current capability of your device. And in the case of function generators, that will manifest as not as high a voltage as you thought you would get, and that's known as voltage sag. So moral of the story is the lower the resistance of your circuit, the lower the load resistor, the more current your circuit needs to have, the more the condition of and characteristics of your source will matter, and the more advantageous it might be to have two sources in parallel if you need to supply the current. Certainly if you are looking at portable sources like an electrochemical source, a battery type source, capacity will be important in having two parallel sources. Even if you have a fairly modest current and either one can supply it, having two, you will supply it twice as long. You'll have greater capacity. So that is it for the demo, and along with this, please check out the other videos that step through these same concepts with the TINA simulator and with some hand calculations.